people wander in when they wander in, because they do. I thought I'd just do a quick recap from last week. The messages from last week were really about understanding performance, and particularly understanding resources and the different characteristics they have. And resources, an ideal resource is something that you can grab hold of at no cost and slice up into smaller pieces as you want to, again with no cost or overhead. That's the ideal. And no real resources behave that way. There are costs in acquiring a resource. There are costs for slicing into thinner and thinner slices. And typically a resource will behave at its best if it's given to a particular application for its sole use for as long as it wants it. And the more you virtualize it and slice into pieces and hand them out, the more overhead there is from doing that. And different classes of resource behave differently. The costs of that slicing and handing out differ with different types of resource, and sometimes those costs are quite subtle. If you're dealing with a processor, then the costs are primarily cache related, that it takes time to build up the caches so that you're satisfying requests, memory requests at the closest to the processor level as you can, at the fastest level. And if you swap to another unrelated application, then all that work you put into filling the caches is gone to nothing, and you have to refill them again. So there's a cost there. If we go to the other extreme and have an old-fashioned spinning Rust disk, of which there are plenty of them around still, if you want lots of terabytes at a reasonable price, that's what you go for. There, the costs are the inherent cost of latency. Just the thing is spinning around, and you have to wait for the spin to come around to you. So you have to wait for that spinning. And the terrible cost of moving the head from one spot on the disk to another, from one cylinder to another. And if you're reading a single file sequentially, for a first order approximation, the heads stay where they are, and you just pick up a whole cylinder. Hopefully you move to an adjacent cylinder and you pick up that one, so that's the maximum speed. In practice, even if you're dealing with a single file, the way the space allocation algorithms are, that you'll read a particular physical extent, which might be a whole cylinder, and then you'll jump off somewhere else. You might, if you're really unlucky, be bouncing all over the place, even though you think you're reading a file sequentially, which is why you have disk defragmentation, to try to take those pieces of things which are no longer contiguous and bring them back closer together so that you're not spending as much time moving heads. But as soon as you start doing multiple applications on the same physical volume, then by default you're moving stuff around. So a typical spinning Rust disk, so a laptop style one, runs at 5,400 RPM. You can back calculate 4,500 RPM into milliseconds per spin. A typical desktop sort of middle of the range disk is 7,200. That's a bit faster, so you'll spend less time waiting for spin. And there's probably an obsolete category now of fast enterprise scale disks, which were 15,000 RPM. But even still, you're still talking about 2 or 3 milliseconds for waiting for the thing to spin, plus the head movement times. So they have very, very bad sharing characteristics. And you think, oh, well, good. These days, if I'm dealing with a volume up to a terabyte or two, or if I'm enterprise stuff and I'm willing to spend the money up to a few tens of terabytes, then I can go solid state disk. All my problems are over. Well, no, because there's caching happening there as well. And if I do a burst of writes, it'll be first of all soaked up in the RAM inside the drive. That's good, as long as the RAM is backed up by battery, so if I lose power I don't lose all those writes, but we assume that's been taken care of. And then they get moved to a faster form of flash, SLC flash, which is at least persistent, so I don't care about memory failures. But that's also a cache, and eventually it's got to be moved on to its real spot. And if I fill up one of those caches, all of a sudden, instead of getting 100,000 writes per second, I'll drop down to 10,000 writes per second. So the caches are there to solve problems of bursts, not to give you more overall capacity. So even with solid-state disks, there are still performance characteristics which might bite you when you hit the capacity of the caches. Sharing characteristics will still be better, but they're not perfect still. I hope you all got around to doing the little lab exercise last week where you did a little bit of performance modelling on what type of throughput you'd get for a hard disk versus a solid state disk. And you found the solid state disk was an awfully lot more performant. Orders of magnitude difference in performance. I put that bit in there just so you could do those calculations again with the solid state disk to see how much difference it makes. But yeah, not perfect. And now we're getting the introduction of the next level of performance, which is the non-volatile memories, which in performance Flash has some terrible performance characteristics. You don't, if you say here write this 4K block to a solid state disk, a flash based disk, it'll fill up 4K of the cache, but to write out to persistent storage, that gets done in much bigger chunks because it's got to coalesce things and the whole page and rewrite. It's really messy, so actually it's quite slow at physically writing whole bits. So we're now getting this new class of non-volatile persistent memories which are effectively block addressable, where I can do a single block write and it takes the time to do a single block write. So, and they're just, in 5-10 years time, they'll be a significant part of the market. So Intel's Optane is an example of that's really the only one which is out there, but there'll be other non-flash type memories coming in the next few years. And they give you very good latency characteristics and don't have these falling off a cliff when a cache gets filled characteristics. And what's just coming out now is saying, yeah, storage is so old-fashioned. Let's just have persistent memory instead. Because to get to something on storage, I've got to go through the operating system's file system stack, which then gets to a device driver stack and goes out through some hardware there and then come back again. So that might add a millisecond to my latency, just going through that software and hardware stack. And when I get fast enough devices, that milliseconds is important because the device is less than a millisecond. So the hard disks have probably got SAS or SATA interfaces on them, which are not that fast. So to support Flash and the things that will come after Flash, we now have specialist NVMe interfaces and things which are orders of magnitude faster again, because the previous ones were not fast enough. So now, when we go the next stage along, you can get non-volatile memories which plug into memory slots and get handled by the memory controller. So we're now talking about latencies in the order of a few microseconds to get to persistent storage. And that changes everything. When I first started hearing good people talking about some of the implications of Flash for databases, we spent 30 years optimizing databases so they give you good performance on slow spinning bus disks. Now all of a sudden you don't have that type of disk anymore. You can put it on something really fast. Well, why do I have all these database structures which are there to optimize performance for something that doesn't exist anymore? So there's some radical ideas about how I might restructure databases altogether. And the next stage of that is, well, I've just got persistent storage. I've got 2 terabytes of persistent storage plugged into RAM slots next to my processor, which is available at a microsecond latency and gives me throughput approximately the same as RAM. So how does that change everything? And the answer is we don't know yet, but it will change everything. So the important thing about resources is that they do have performance characteristics, and you really need to understand them because they reflect the way your system is going to perform. And caches are fun to play around with. None of you are scientific computing people, but the people who go and write the large code bases for scientific computing really, really care about this stuff, because they're doing huge workloads and small things can make big differences. If you can get that algorithm, that core piece of that loop into the fastest memory, the L1 cache, then it might run 100 times faster. So instead of something taking 100 days, it might take a day to run. That's a big saving. There was a piece of code I wrote for a paper where I was just going through some arrays. And if I swapped it so that I went through the array column-wise rather than row-wise, it ran 10 times faster. Same code, same number of operations, I just switched the way I was going that way rather than that way. And that's because all of a sudden a whole row fitted in a cache. So I picked up a whole row of my matrix, computed with it, whereas the other way I was hitting one, going out to main memory, hitting the next one, going out to main memory. So just little things like swapping orders could make an order of magnitude difference in performance. So scientific computing really care about that stuff. Okay, on to today's talk. So we're going to go down this week and next week. We're talking about the glue, the networking layers, and architectural impacts of that. So this week, although it says message-oriented middleware, that's a bit of a misnomer. We cover a bit of that, but we're going to be talking about messaging, and next week we talk about some of the protocols in this space in a bit more detail for protocols. But one of the lessons I wanted to get across, and I'll say this multiple times, there are, at the base level, everything is a message. And then with a message, you have a choice of waiting or not waiting. So they're the two things, messages and waiting. And various combinations of those give you everything. So the stuff we started talking about, the stuff you've been dealing with so far, is all synchronous. And if I'm calling a local method, it's synchronous. You know, I call the method, and the hardware swaps over to running the process swaps over to running the thing I'm calling, and when it's finished, it does a hardware return back to me. So I wait because I no longer have the current instruction pointer in the processor. It's doing what I'm asking it to do. So I wait by default because the processor is busy running the code I ask it to. So the model's synchronous model. I make the call, I wait for the reply, even though I'm waiting in this case because the processor is doing something on my behalf, and then I get the response back, and that's a single operation. That model was carried through by some people into distributed computing because it's a nice, simple model. Simplicity is really important. Everyone's familiar with it. So I make a remote call. I now have to wait for a reply with some type of wait. Someone's doing a wait for me because I'm not running on the same processor anymore, so the processor isn't busy doing something else. So I physically wait for a reply, get the reply, and I continue. The waiting is happening at some layer down in that infrastructure. And because it's now remote and I've got to wait, then I've got to worry about handling timeouts or the possibility I might wait forever or whatever. So there's some exceptions to handle there. But it's great because it's really easy to use and familiar. Of course, there's no reason why I have to do asynchronous, why I have to wait. I could send the request out and do something else. And then when the response is available, I can pick it up and do something and process it, as well as handling all the exceptions that occur. And that's the fundamental asynchronous model. I send out a request and do something else, and then when the results are available, I continue. I'm being very vague about when the results become available because that's a complex question. And the interface into this async could be exactly the same type of method calls as I had above. It's some magic async flags I can put on things saying that's the way it wants to be. There's a whole lot of ways of making async calls, Or it could be some type of explicit message passing interface, an API which says put a message and get a response. And people write lots of systems based on those types of APIs. But they're effectively equivalent. They're just APIs. They're just conveniences for you. Some of them might expose more things or less things. If I'm doing this API, the procedure call type model, then I've got all the complications about what attributes I want. You've seen the WCF model, they're all done by magic decorations and config files and things. It looks like a method call, but lots of stuff around it saying, by the way, this is really something special. It's not really a local method call, it just looks like one. And in the explicit messaging, I might have an API where I say, get me a message, container, I populate it with the message, we've got some way of describing what the message should look like, and we'll have attributes on there saying how to behave under certain circumstances. So things that in the RPC type model might be done by attributes and configuration, in the explicit model might be done by calls or parameters on the methods you're calling. But they're all the same. What is probably more important is message exchange patterns. So we've got two things. Let's call them a client and a server. We can call them A and B if you want to. And we've got message flows. And the simplest one we just talked about really, is request reply. In that pattern, I'm going to send a request out and I'm going to get a reply. This is not the same thing as necessarily synchronous or asynchronous, but I am going to send a request and I'll always get a reply. That reply can include results and it can include exceptions if something went wrong. It's sort of inherently synchronous because there's this idea of request and reply always being coupled together. There is one way where I say, send a request and I don't expect a reply. In fact, I can't get one. There's no way of getting a reply. I just say, here you go, have something. So if I was writing a system that was logging something, for example, and I want it to be really low overhead, I just want to send it out, get it logged. The logging thing works almost all the time, and I don't want the overhead. It can happen in the background as far as I'm concerned. So, good one-way communication. We'll come back to one-way. And duplex. With duplex, instead of really having a client and a server in relation to that, used to call them master-slave ones when it became politically incorrect. So peer-to-peer, that they're both equal partners. So I send you a request, and then you send me a response as a peer. So you're not replying to me, you're sending me something back. So it's a peer-to-peer relationship. And if we're doing the WCF type model where we have contracts, in the request reply model we have a single interface. So let's go over to the right hand side here. So this is some WCF for these various things. So we've got the default attribute is request reply. So I've got a method called hello that I call, passing it a greeting string, and it returns a string to me. And that first case, we get a result, which is the string. So I say hello and pass Paul, it comes back and says, hello Paul. It's cool. The fact that could fail for some reason. It might not like whatever I passed as the greeting string, for example, and might return an exception to me. When I've called hello, I will get instead of getting the result string, I will get an exception. But is part of the reply. The second one there is again request reply, but there is no reply. Meaning I'm still making the request, but the reply is either everything went okay or I had a problem. So I'm still getting the exception back when I come back from making the call. So I still make the call. In that second case, I don't get any value back from the call, but I know the call has been made and I know it's been successful because I would have got an exception there if it hadn't been. So I can, that's a request reply even though it's got a void result. The one way I tag my contract operation with is one way equals true. And so I've told it this is one way, you go and call hello, passing it something, crickets. What happens is it goes down, goes through various WCF layers, goes through networking layers, gets pushed out to the network. That's it. End of connection. Gone. So if anything happens, if I get a failure on the way down through the networking stack on my side, I'll get an exception. But once it's out onto the wire, I don't know about it anymore. So it's one way. I've sent it. It's on its way. It's gone. So
essentially difference between the second one and the third one, right?
Yeah. So the first one I can get an exception. Second one I won't get an exception from the server side. From the server side, yeah. I can get an exception from the client side before it gets sent out. Once it's out there, in the second case, there's no return path.
And the third also the same as the second.
So, the last one, duplex, peer-to-peer. So we're going to, the caller calls his peer by sending a message, and the peer calls them back. So instead of a call and reply, we effectively have two of these one-ways in parallel. So I call you, and then when you want to pass me results back, you call me back. So we have two service contracts. There's the one from the client to the server, the calculator interface, and there's the one that the server uses to call me back to pass me back my results. So totally symmetric, contracts on both sides. And this is inherently asynchronous because I make a call to my peer saying, here, do something for me, and some other time it'll come back and say, I've done it for you. So they're the three different message exchange patterns. So the normal request reply is obviously the simplest. Let's go. I've been glossing over a few things because they're complicated, but the question is, what on earth does callback mean, and how does my poor little bit of client code know when it's being called back? That's a very complicated question. There's a problem with all async stuff. It can get quite complicated, which is why request reply is so simple, because I send off the request and I'm still at the point in my code where I can process the reply. I do the call and I'm still here because I'm waiting at the spot where I did the call. Whereas in that full duplex one, I make the call, I go away and do other things, and then somehow the results come back to me, and I could be any piece of code at that point. So now I've got to resynchronize in my code and say, I've got the result of that calculator call I did a while ago. Now what can I do with this? What was I in the middle of doing when I made that call? So it can be complicated to writing async code in that way. You've then got to reconstruct the state you want to be in to handle that response, perhaps. It might just be get the response and put it on a screen and throw it to the user. That might be the response. So the synchronous stuff, you get a tight coupling between the two parties, and both of those parties must be available and active at the same time. I can't call someone who's not there, which means that calls can fail. I try to call the server, not there. The caller will normally wait. So The message patterns and sync and async are different animals. People often will conflate them. Lots of things people conflate, but they're different animals. Conflate means sort of pushes things together. So it is perfectly possible to write async code around this sort of request-reply model, because I can do something and tell the system, I'm not waiting for this reply. And there are mechanisms in the programming languages so you can later on say, is that reply ready now? And pick up from where it was. So you can force async programming even in a request-reply model. It just takes work, and you have to put the effort in. So normally you wait for the response to come back, and this really forces you into a simple one thing at a time model. So there's an example in one of those references, perhaps, or one of the things you can find from one of those references, where someone says, let's write a piece of code which makes breakfast, makes the full English breakfast. So I want to fry some eggs, fry some bacon, toast some bread, juice some juice, make some coffee. They're all the things I want to do. And if I was doing that using that synchronous call reply, I'd say, make the juice. Wait for the juice to be done. Good, now I've got the juice. Cook the eggs. Wait for the eggs to be cooked. Cook the bacon. And do them one at a time. Now that's obviously not a very good model. And what you want to be able to do is start all of them at once, and as they complete, you build up a picture of what's complete, and when they're all complete, fine, then you go and eat your breakfast. So that's a much better model, but you can't do that using synchronous request reply because it just doesn't support you. So if you want all your server requests to run in parallel, then we're going to need a different model. And yes, with additional programming effort, you can do lots of async stuff, but it's harder. Whereas with that full duplex model, then no reason, the things I'm doing here are cook bacon, fry eggs, toast bread. They're the operations I'm calling on the server. And each one of those I say, go ahead and do it. So I can do start of all the stages of my breakfast in boom, 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 boom. The server's away doing them, and it calls me back saying, toast is toasted, eggs are cooked. That's my callback. And when so I gathered all those bits of information with a little table. Oh, good, the eggs are ready. Okay, everything's done now and complete. So you can see with that full duplex model, I could do that parallel breakfast cooking, which I couldn't do with that easily with that request reply model. Oh. Yeah, that's good. So, good. Making sure I haven't just said everything already on the slide. So let's get back to the bit more on the one way. So, definitely asynchronous because there's nothing to wait for. Right? So it's absolutely asynchronous. You send the thing on, you get your call finishes when it's written to the network, but there are very few guarantees in this world as well. I don't know whether that message gets through to the endpoint. If I do care about that, then I better worry about it. If I do send message, send message, send message, does the server receive them in the same order that I sent them in? I sent message 1, 2, and 3. Do I care if it gets them as 1, 2, 3? They're going over a network. Things happen on networks. Packets go past each other. They get delayed. They go by different paths. It's possible that I could send messages 1, 2, and 3, and the server would receive 3, 1, and 2. Perfectly possible. That might be important. It might not be. There are techniques. So now going down a layer. So that's the message exchange pattern. What we haven't talked about yet is what the transport layer is doing. So it might be the transport layer might fill in some of these gaps. So with that example I had before with the one way, I might say, I want you to send this over a transport which is implementing a reliable messaging service. And magically, I will get those reliability and order delivery guarantees because the transport layer is doing it for me. And moving on from there, we can get even more reliability by running over a queued messaging service. So before we just assume we've got a network there, we drop a message over TCP port, boom, it's gone. Well, there can be layers in between there, so I can build a reliable messaging service or a queued messaging service on top of those underlying messaging services. And they give me useful attributes that'll make my life easier. So I might be able to use reliable messaging, gives me good end-to-end delivery guarantees, and queued messages even let me run while the thing I'm talking to might not be available. So the decoupled means there is that instead of us both having to be up and available at the same time, I can break that linkage and I can send message to you, and you're not listening. That's cool. When you do listen again, the messages will be there delivered to you. So I can break that problem I had with the previous one where we've both got to be available at the same time. So decoupling is quite valuable. In the very first lecture I had a hairball. There's things everywhere. Imagine how hard that would be if every single one of those links had to be constantly active and available. And the chances of some component somewhere failing, and then how does that failure propagate through? Can that fail, and that fails, and that fails? You can imagine that happening. But if we can decouple those components in some way, it might be a much more robust system. Architecturally still the same, but we've now got a level of decoupling between the components. The duplex pair of coupled one-way interactions and then with two interfaces, and that's a really general model and inherently asynchronous with all the complexity that causes, but it certainly means I can issue multiple parallel requests to multiple servers, but then I've got to go and bring all the results back in again in order to continue in some way. Queued messaging. Very successful model. So I've got a sender and a receiver. You can call them a client and a server if you want to, but we're moving into a world where we call these things senders and receivers. And they're decoupled via queues. These queues are one way. There's a queue from the sender to the receiver. That queue, messages don't go in the other way, they just go sender to receiver via that queue. If I want to send messages back from this receiver to the sender, I have another queue. Each queue is one way. When I want to send a message from the sender to the receiver, I write my message to a local message queue. Not to the network, to a message queue. And then there's some little daemon running around in my system which picks up messages off that queue, traverses the network and drops them in a queue on the receiving side. And then there's another little daemon sitting on the receiving system which will take care of delivering to the applications. So 3 steps: I write message to local queue, not to the network. The message service transfers the messages from one queue to the other queue, and then the receiving app picks it up from their queue. Totally decoupled. If that disappears, if we can no longer get a link between here and here, the message just built up in this queue. When the message daemon in here can establish the link to the message daemon in here, then those messages will be taken out of that queue, transferred across. So we can cope with network failures, no problem at all. It's really good. Sometimes called a send and forget model. We say, send it, and that's it. I don't care anymore. It's going to be sent. I know it's going to get there because I trust this messaging layer. So, queued messaging, really cool. There's a very small version of that spaghetti we had earlier on. So here we have a central office. It's got main system running everything. It's got webby stuff and local stuff, but it's got remote warehouses and remote sales offices, and they run their own systems. In the previous version of this diagram we had weeks ago, these were probably RPC calls, synchronous RPC calls. which means that there's a lot of things that the remote sales office can't do if it can't connect through to here. It can't say, make a sale, because it can't talk to the bit of head office gear which is taking care of implementing the sale and pushing it across to the warehouse and deliver the goods, because that can't happen. So if that link there is down, that remote sales office doesn't work. If we go to message queuing, they're now decoupled. So I can continue, as long as I've got access to cached copies of important data, I can continue running even if that network link is down, and when it comes up again, my sales orders will push through and get processed. So lovely decoupling, and so it's now a more robust system. Let me backtrack on something I just said. So you think, oh, this is really cool. Send and forget. Now I want to send this message to that machine. So I drop it in the queue, and I've got reliable messaging, and queuing is great. It's going to get sent. Possibly. Because things can still happen. So it's possible that even though it's called guaranteed delivery, you have this sort of send and forget model in your mind, there's always the possibility that there will be a failure. So, and instead of that failure happening on the spot, it might happen days later. That's okay. But it might be easier to get the exception on the spot, but you don't get that. We'll talk more about ways of handling some of this later on. So what we actually get is we get guaranteed delivery, meaning we try really, really hard to do the delivery, and we'll recover from lots of things that can go wrong. But at the end, there's no guarantee. It's only we'll try really, really hard, and you still could get a failure of delivery. So there's like a deferred exception, but it's probably going to be handled in a different context or a different process to how I process it was on the spot. So it might be it gets pushed off to a program whose job it is to clean up the mess, or to a person whose job it is to clean up the mess. You know, these sales orders didn't go through because there was a problem with them. They caused the server application to crash. You need to fix them. So, but what we won't get is all those nasty things about, oh, it's not available just now, I had a networking issue here. A lot of that complication will be taken care of for you. So, messaging, reliable messaging, queuing turned out to be a really, really good idea, and highly popular. You can break your application up into chunks. They can talk across queues. The chunks can be running on different machines. That async model where so if you go back to the breakfast, we can now have two applications, one responsible for ordering the breakfast, and the other responsible on the client side for saying breakfast is ready. So we've got two queues. One queue is the orders from the client to the kitchen, and the other is from the kitchen back to the person responsible for serving, saying the eggs are ready, okay, go and pick them up. So two separate processes, because the one placing the order is not necessarily the process that wants to pick up the things from the kitchen shelf and take them out to the customer. So that's cool. So you've got two separate processes, and they're neatly done with two separate queues between them. So we can, and also there's quite sophisticated technologies there, so we can do lots of cool things. We'll talk about them later on in this lecture. And along with that decoupling, I don't really care what's on either end of the queue, as long as the two messaging daemons know about each other and can pass things between each other. Then there's not as much technology dependence that the it's possible that someone can do some magic and say, this is a Java system, this is a .NET system, and we don't know or care because the queue in between is masking those differences for us. So that's quite nice. So we've got the tarball, or even the previous slide we had there. Now there's no need for technology uniformity there. We can put isolation barriers between the pieces via these messaging queues as well. Sometimes this messaging stuff is called MUM, message-oriented middleware, just because that's what it was called. The features, it's inherently asynchronous. The sender and receiver are decoupled in time. You send messages, you don't know when the receiver is going to receive it. It won't be necessarily now. It could be a week's time. They're decoupled in time. If a week's time is okay with you, that might be a good thing. So they're decoupled, they're not synchronously linked. They have this lovely send and forget attribute, and the two next attributes are really important. Transactional attributes and persistence. When we were talking about transactions several weeks ago, I said transactions are not just about databases, they're about resources. And we talk about transactional resources and transactional resource managers because we want to be a bit more general than just a database. These message queues can be transactional resources, which makes life very easy as well. So with a transactional message queue, when I say put the message to the queue to be sent out, it gets put in the queue with a little tag on it saying, don't send this yet until the transaction's been committed. And if the transaction aborts before it's to commit, the message gets taken off the queue again and never gets sent out. Whereas if it was a straight comms link, like the WCF calls we've been doing, you say, here, send this, and it'd go out, and they say, oops, I'm sorry, I didn't mean to send that. I've rolled back this transaction. That doesn't happen with transactional messaging here because the queue write operation is part of the transaction as well. So we don't actually physically allow them to be sent until the whole transaction has been committed. And that's quite a nice feature. And similarly on the receiving side, I say, get me a message to process, an operation request from that queue to process, and I'm processing it and something happens, I get an exception and need to roll back the transaction, the message goes back on the queue. It's not lost, it gets put back on the queue and then I can try it again. So really, it makes life a lot easier. A nice feature. Persistent is a bit like the durable in the ACID transactions. It says these queues are not just in memory structures, they are persistent across failures. They're logged, they're kept on storage, and if I'm sending messages, let's go back to one of these pictures, I'm sending messages from here to here, there's 5 messages queued up here for this receiving app to process, and this machine falls over. Boom. With persistent messaging, when this machine comes back up again, that queue and the messages it contains will be restored. So this application comes up and everyone's cool. And because these two are decoupled anyway, this guy doesn't know or care that had a problem. It asks these things to happen, and when it's processed them, the response will come back. It might take 5 minutes longer than it would normally, but you don't know or care. So we've decoupled them, and the persistent means that either side can fail, and on recovery, the messages will still be there. That's a good feature. Okay, I think we've probably talked about that. Basically, I don't know, I see what to say there. So, because there's a lot of confusion in this area. So, this diagram differs from the previous diagrams in the previous one had 2 of these queue structures because I was doing distributed work. But the fundamental model is that I have a queue, one queue. But the queue might be split across multiple machines, or it might be a single queue. And what we had before was a single conceptual queue, which was implemented by having 2 queues, one on the sender, one on the receiver, and some pieces of code that transferred messages between them. That gave us the decoupling. But conceptually, it's still just one queue, and messages will be in one of them or the other, and they'll be transferred between the 2 of them. So this is the same picture, except we've pushed the queues together because there's only conceptually one of them. And our operations are put message on the queue, get a message from the queue, and they're independent. Cool. Persistent queues. So now I've got storage backup for my queue. When I put a message to the queue, I not only update the data structure here, but I do some type of acknowledged write to storage. Now, I talked about acknowledged writes when I was talking about the durability in transactions. It's not good enough to say to the storage subsystem, here, write this, because operating systems lie to you. They, oh, I'll put it in buffer, I'll put it in memory, I'll buffer it, I'll get around to it later. Which is not what you want. There'll be flags in the I/O system saying, I want you to write this, and I want it written. And so there'll be some type of I/O sync flag on that write. It's an acknowledged write. So the little guy taking care of this messaging will not say it's in the queue until it's physically in that storage. And of course, just adding something to an in-memory data structure, a queue, versus doing acknowledged writes is enormously higher overhead. I didn't include some studies that Ian Gorton and I did when Ian Gorton was still here before we were traipsing off to the US, where we looked at the costs of these attributes. And you could get 2 orders of magnitude drop in throughput by turning on the persistent option. You didn't lose them if your system failed, which is a good thing, but the throughput dropped enormously. I didn't include them because they were done on spinning Rust, and you wouldn't even think about putting those files on spinning Rust these days. So the cost would not be 2 orders of magnitude. It might only be 50% now, or it might be 1 order of magnitude. It would be a lot less than it was then. So, and when we were doing those tests, there was a real cute thing that I was using MSMQ and IBM's MQ series and TIBCO, and worked out that what MSMQ was doing was, if we were in this situation where we had the daemon here talking to the daemon here of an active network, and I said, write this to a persistent queue, it never went into the persistent queue on this machine if it could talk to the other queue. So the messages went whoop, whoop, over to here straight away, because all you care about is written. So I did the RPC call to the other daemon saying, can you write this and guarantee it for me? He said, sure. So why bother writing it here and writing it here when I can just write it straight to the remote machine? So that was a nice optimization, which reduced the overhead by half, obviously. I didn't have to do an acknowledged write here, then pick it up and send it across again. So that was a nice optimization. We're wondering why it was not working the way we expected it to work. It was smarter than we were. So, great improvement in reliability and robustness, but of course it's costing you performance. Okay, not much to say on this slide. Some of these slides I've rewritten completely, and others I've kept from Alan. This is one of Alan or Matt's slides. Only a couple of things to say here. This is a request response system. So we've got queues this way, queues that way, a pair of queues, because they're one-way queues. So 2 sets of queues, and then we have here we've got something which is the software implementing this remote queue, the reliable queuing system, and it does things for you. There'll be admin tools for it, and in the prac you should be able to go and look at some of those admin tools and see messages queued up and waiting. They're persistent, so we can kill things and the messages will still be there. So someone's got to monitor that. Yeah, there's useful things and admin tools for this messaging layer. And that's about all that really is said there. Okay. Here's where people start getting confused. The fundamental messaging model is point to point. If I'm doing between two systems, I've got two systems. Both systems have queues, and the messaging daemon on one machine sends a message directly to the messaging daemon on the other machine. It's point to point. No intermediaries. This guy wants to send a message to this guy, so it goes whoop and sends it to this guy. It's all point to point, peer to peer. That's the fundamental model. That's pretty obvious. There's no intermediaries. Yeah? Just message queue to message queue. And so each of those little pink boxes has a messaging daemon on it. It's running the message queuing code. That's fine. The reason I'm saying this, and it seems obvious, is there's a whole lot of models where people think, oh, if you're doing messaging, you have a messaging server, a centralized, in the middle messaging server. And that's been a popular model, particularly in the Java world, but it's a different model. The fundamental model is just peer-to-peer, but there's no reason why you can't do this as well. Now, we're still doing messaging, we've still got the apps over here, but the queues are all in some central messaging server. It might be a separate box. If I've got lots of applications talking to each other over queues in my same box, it might be running on the same box as me, but it's a central piece of code which does all the queuing work. And then the various client applications talk over RPC, or an equivalent, to that central messaging box and do it. Same model, but now centralized rather than distributed. And that's, yes, it's been quite common, particularly in the Java world. And the obvious problem with that is that that's a central point of failure. Whereas that distributed model, they're all individuals. So if one of them goes down, well, it affects that link there, and if they're reliable, nothing much happens. Whereas here, if that fails, the whole system's dead. So the participants are no longer autonomous. They're now dependent on that messaging box. I'm always a bit puzzled about why this took off. I suspect it's sort of ignorance, like most things are. And it's people got introduced to it via something that did that before they thought that's the way the world was. But if you go back to the original products like MQ Server and Tibco, they're all point to point. And then the Java world went this way. Okay. A couple of things to say there as well. Of course, as this is now a central point of failure, as we'll talk about a bit later, there's a slide on it, then there's all the things you can do to handle single points of failure. You can do clusters and you can do failover and replication, etc. So now you've introduced a central point of failure, you have to use the techniques we have to handle single points of failure in order to make it robust again. So going back to the messaging pattern, this is fundamentally duplex because two queues, the two contracts, and I talk to you, you talk to me, it's fundamentally duplex, but people still use it for synchronous. So there's no reason why you can't use this messaging infrastructure and say, send a request, wait on the response queue for the response. You can write synchronous code using this messaging, effectively asynchronous messaging interface. So you send the message, you wait for a reply message, you do a get call on the response queue, and if the queue is empty, you wait for a message to arrive in the queue, and that's all fine. Why would you do that? Because it's there. If we've decided that we're going to build a whole enterprise architecture on messaging, use messaging. If it makes sense to you to do something synchronous, it's okay. You can do the message exchange pattern is not the same thing as the transport layer. So you can do a request reply message exchange pattern on top of this thing, which is effectively an asynchronous full duplex transport layer. No problem at all. So queued message is a transport layer, not a message exchange pattern. And a lot of, nor a programming model. And people will get those two things confused. But just keep them separate in your mind and it's all fine. Ooh, transactions. It's a bit on transactions. So I said that the queue is part of the transaction. So begin transaction, update a database record, put the message on the queue, and then commit. So those two operations are part of the same atomic transaction. If we fail before we get the commit, that gets undone, that gets undone. And on the receiving side, we do a get call, suck it into the application, we do some database updates. If we don't get to the commit, that gets put back onto the queue and that database update gets undone transparently. When I was talking about transactional resources weeks ago, I talked about this problem, a little bit of code where someone wants to withdraw some money at an ATM, and we do the account database, the update stuff, and then we need to tell the ATM to issue the money. And no matter where I put that networking call, it's a problem. If I put it inside the transaction, and then the transaction fails to commit after I've sent out the message to the ATM, then the ATM has issued the money for a transaction that's rolled back. If I say, I shouldn't be doing that inside the transaction, I do it after the transaction, I update the account, the money is no longer in the account, and then I fail, and the message hasn't been sent to the ATM, so the customer doesn't get the money. So either way, we're in trouble. You can imagine if the message queue on the other end of when I'm doing if this thing here was the ATM daemon, it's sitting there picking requests off a queue and then pushing them out to an ATM with some protocol handling to the ATM, so there's acknowledgement of the request, etc. Then I update the account, put the message on the queue to tell the ATM to send out the money and commit, then that solves that first problem. And then I write some very special code over here which picks that request to send the money out through the ATM, picks it off the queue and talks to the ATM and etc. But does all that inside a transaction boundary, so if something's gone wrong, it gets put back on the queue and it can think about doing it again. So we could have a go at addressing that problem using transactional queues. It'd be not a bad basis for solving that problem. Talking to the ATM would probably be quite tricky, but you could do it. I've got a nice slide for that. Yes, I do. Okay. The sender and receiver, let's go back a slide. Sender, receiver, they're both transactional, but they're not sharing a transaction. This is a transaction on this side, this is a transaction on this side. They're two separate transactions. They don't share a transactional context. The queue is the transactional boundary. So, two separate transactions there. a rollback on the receiving side has no impact whatsoever on the sending side. It's already committed, commit has happened. So if I build a synchronous model around here, request reply, if I was doing it using some other synchronous technologies, I could wrap it all in a single transaction. Here, if I'm going send the request, gets picked up by the server sends a reply, that's 3 transactions, not just 2. First transactions put the request on the queue, second transaction get the request and send back the response, and the third transactions get the response. So this has probably got nice builds on it. There's our 3 transactions. T1 update the client database, send the request. T2 server side, pick up the request, update its database, send the response, and T3 is pick up the response and update the database on that side. So there's transaction 1, send the message across. Transaction 2 includes removing the message from the queue, updating the database, and sending the response on the other queue. And there's sending the response, and there's transaction 3. So although it's request reply, it's 3 separate transactions with their own transactional boundaries. That must have taken me ages to do that slide at one stage. So I'll talk about the next slide, but I won't have it up there just now for a second. So do any of you think about the problem I talked about, transactional messaging, and on the server side, the receiver side, I pick the message up off the queue, I do some stuff, I generate an exception, and the message goes back on the queue. What happens then? I pick the message up the queue again, and I process it, and hopefully this time I don't get an exception. What happens if I do? I generate an exception, I abort the transaction, I put the message back on the queue. That could be a bit of a problem. So of course there are techniques to handle that. They're called poison messages. So someone had fun giving up the names of this. So we've got poison and poison messages, and we have dead letters. And they're the technical terms that people use. So we'll do because I just started talking about the poison, I'll talk about the poison first. So we put things back on the queue. Quite reasonable, because it might have been something like a deadlock exception, or some other resource. I'll try it again. Things happen, Most of the time it'll be okay the second time. So that's a good thing to do. But if it keeps on doing it, then what we're going to have in our messaging system is a little counter and a retry limit saying, I'm sorry, you can only try reprocessing this many times. And if it exceeds that, then when we roll it back, we don't put it back on that queue, we put it on a poison queue, a special poisoned messages queue. And then they're no longer part of that normal workflow, they're off all by themselves. And then you can have another application whose job it is to go and open the poison message queue and look at them, because this is obviously a really bad message. It's causing my application to crash. So it needs diagnosis at least, or special handling. And there might be some customer request involved in that dead message we might want to take care of. So diagnosis, administration, so that type of thing can happen. And there's quite a reasonable write-up of that and those links there. I said before that reliable messaging doesn't really guarantee delivery, it just guarantees it's going to try really, really hard, and it's possible that messages will not be delivered. I send you a request, and for some reason, it never gets delivered. Something's happened. So what I'll do in that case is put when I'm sending the message out, it will have a little thing saying, this message has to be delivered within this much time. And if it's not delivered by that time, then it will be put onto a dead letter queue, another one of these special queues. They're called dead letter queues, from the dead letter office at the post office, where the post offices have a place where they mail they can't deliver, the dead letter office. and then again you can retrieve them for postmortems and fault diagnosis or recovery in some way. So they're the technical terms: poison messages and dead letters. So an example: MQ series, fine piece of code. Point-to-point message queue architecture. We have queue managers taking care of communication between distributed queues, persistent and non-persistent messages, and transactional queues, and they use a standard there called XA. There are a bunch of standards in this general space, in the RPC space really, and the XOpen standards for RPC, but there are distributed transactional interfaces there, and there's an API called XA. So it uses the XA interface, which is good because now MQ can participate using a standard in a transactional context. So that's a good thing. It's got persistent and non-persistent queues. Non-persistent queues, obviously, if I lose the node that the queue is on before it's been read, then it's gone. Non-persistent. It supports message priority, so you can say this message is more important than these ones, so we'll drag that one off the top, and transactional support. Another example, MSMQ. MSMQ, I suppose, was heavily influenced by MQ. They even got the MQ in the name. It's a standard part of Windows. It's either on the lab machines you're going to be using tonight, or you'll have to configure it in, but it's a standard part of Windows. It's like MQ series, it's point-to-point. It offers persistent, transactional, and it's got pretty conventional send and receive APIs, and it's also supported by WCF. WCF has these things called transport bindings, and we just say, here's the WCF layer, and underneath it for transport, I want you to use MSMQ. So you're not doing much, you're not changing your API, you're just saying the transport layer is MSMQ. So we use the net MSMQ binding. So that takes our RPC-like calls and magically maps them onto MSMQ messages that are put on queues, etc. And it's got exactly once and durable properties. Exactly once is a reliable messaging. It also supports transactions, I should have said that. And durable means persistent. So but the actual words are durable for persistent, and exactly once is reliable messaging, meaning that the transport layer is guaranteeing that when I send you a message, it will arrive and you will only get exactly one copy of it, and the messages you send will be received in order. So they're all reliable messaging properties, which are the magic word on the pigeon droppings for the definitions are exactly once. This follows on what I said before. If I've got that centralized model, then I have to worry about the single point of failure. So I might have a pair or multiple of these. It might be a clustered system like I talked about a few weeks ago. And on two of the nodes on the cluster, I'm running the messaging servers, but the cluster is regarded as a single resource by the applications. But they're sharing the work between them. And if one of them falls over, the other one picks up the entire workload. That's great, but there can be complications if I'm sending to this, and sometimes my messages get processed by this one and sometimes by this one. Then am I guaranteeing in order anymore because I've got two machines handling the load? So yes, it solves a problem, but it introduces more problems. JMS. The Java world has a messaging service called JMS. But as everything else in that world, it's an API. JMS is an API to messaging infrastructure. JMS is not a Java messaging service, it's an interface from Java to messaging services. So perhaps the JMS is a confusing word to use. So JMS is supported by lots of messaging service providers, because if you're in the Java world and you want to use messaging, you use JMS to get to it. So MQ series supports it, TIBCO have swiveled around on a heavy JMS supporters, and there are lots of JMS only messaging vendors out there. But it's an API, it's not a service in that sense, and it also doesn't define a protocol. You don't know what's on the wire, you just know this is how I talk to the messaging service I've chosen. You don't know what the messaging service is doing, because that's not part of the
So if you configure
API.
the data and all that,
Yep,
you
yep.
have to configure that within the framework.
Yeah, they understand. There will be the dead letters are another queue. So if you're
within TIBCO, for example.
yeah, there'll be a queue there that will magically be created and things we put on it. So, and the same with IBM, the magic queues, system queues. But so JMS doesn't define a protocol, so there's no guarantee of if I've got a JMS interface to MQ series, that's cool, I can do that, and I've got TIBCO running as well, it's got a JMS interface. That doesn't mean the IBM MQ and TIBCO can talk to each other. I'm talking to the messaging service via JMS, but that doesn't guarantee my messaging services are interoperable, because it doesn't define the protocol. But that's okay, they'll just say, just use one. Standardise on MQ or TIBCO or whatever. So, summarise, ending this conversation. So, messaging. It's highly attractive. It makes some complex application architectures much more viable. Loosely coupled, scales well. The things like TIBCO and MQ and MSMQ are very high throughput, particularly if you don't ask for too many fancy quality of service things. Widely available, but yeah, it's a good technology. One question we haven't talked about, we talked about messages. We haven't talked about what messages look like. They're just messages. And that is another can of worms. You might find that these days often they'll be XML. So someone's defining a schema for the messages, and in the web services world there might be standard ways of describing those messages as well. So there are some standard ways there, and there are also lots of proprietary ways as well. But that's at the plumbing level of the messages. Let's go up a level and say, I want to order eggs. How do I order eggs? What's an egg order request look like? You've done some work on messaging for the prac assignments. So you've got requests, and what do they look like? Who's defining those? How do we know how to order eggs? What's an egg order look like? And we'll come back to that after we do this pub/sub stuff. Okay, pub/sub is a programming model. Publish, subscribe. It is unrelated to messaging, message queuing, although it can be built on top of message queuing. So, commonly is. I've mentioned TIBCO a couple of times in the last couple of slides. TIBCO is a technology vendor. TIBCO stands for the Information Bus Company, and they made their life by doing messaging, and particularly pub/sub messaging. They carved out a nice niche of pub/sub messaging. So pub/sub is a very loosely coupled model. I've got publishers and subscribers. That's why it's called pub/sub. You can think of it as a client with an unknown number of servers. So the publisher publishes something, a message, and that message gets sent out to all the subscribers for that message type. So you can have events or messages. So the service publishes messages, the clients subscribe to a message feed, and when messages on that feed get published, they receive them. So it's probably best to go to the, there we go. Nice picture there. So we have this idea of a subject. You could think of it as a bit like a queue. So the publisher might create the subject, it can then publish on them. The subscribers have two operations. They can subscribe to the subject, and then they can receive messages published on that subject. So I said TIBCO, one of the things TIBCO did very well in was trading and financial stock exchange stuff. Because there you can imagine this is something which is sending out stock prices. These are stockbrokers. So the message published is, I have an order for 500 BHP shares. And it gets sent out to all the brokers, and they can act on it or not act on it. So it's a natural way of broadcasting these messages out to a collection of interested subscribers. PubSub's a nice model. What's there to say on this? Right. I'll come back to that previous slide. So some of the implementations have basically have a hierarchical topic naming system for the subjects, and then you can subscribe to Sydney Support Group, or you could subscribe to Sydney Support Group information, and you could publish on that or that. If you published on that, then anyone subscribed to that would also get it, because it's the next level up in the subscriptions. So, and people support wildcards in it as well. It's all just text. It's no problem. So someone is taking care of looking at, when you publish a message, you say what the subject is you're publishing on, and someone is taking care of looking at your subscriptions and working out whether this message is appropriate for you. So the tree, topic, I'll cover all that thing. So TIBCO was one of the earlier implementers of this type of technology, pioneers in it. It's funny, there was two sort of worlds. There's the TIBCO world, which is sort of event-based distribution-y stuff, and there's the message queuing world. And they're really quite different. But for marketing reasons, they went together. So in the TIBCO world, which is really meant for this lightweight information dissemination stuff, then it makes no sense to worry about transactions. It makes no sense to worry about persistent messages and things. They're just not part of it. But customers wanted to say, we want one messaging infrastructure in our organisation. So some of our applications need these attributes. Oh, well, we'll implement them for you. And conversely, the message queuing people adopted PubSub because it was a useful model. And if your company has decided that MQ series is the way we're going to architectural foundation for our systems, then if we want to do a PubSub model, then we're going to do it over MQ. So the two systems are sort of fundamentally very different, but they just sort of come together through marketing-driven forces. The demand is there. Yeah, so TIBCO, nice, clean, PubSub-based system. So I'll just everything on that slide I'll do from here. So this is a local, on a LAN type PubSub, not a wide area network. The wide area network is the next slide. So we've got a little daemon In TIBCO world, it's called RVD. It's the whatever RVD stands for. The D stands for daemon. And so the publisher wants to publish a message. It calls on the RVD, puts the message on a queue or something. The RVD picks it up, and it somehow or other sends that message to every other RVD on the LAN. And it could do it using, send a message to this RVD. It could know all the RVDs are there. They could have done handshaking and hello, I'm a new RVD. Oh, welcome. So we know about each other. That's all cool. So we could do single cast and send the message to that one and to that one and to that one. Or we can use multicast, which is a networking technology where we say we're doing that. Send this out to all the subscribers at a IP level, at a networking layer level, the IP multicast. So what I've got to do with IP, if I've got multicast enabled on my LAN, is write one copy out to IP multicast onto the LAN, and then because it's on a LAN, they'll all see it at once because it's physically on the wire, and the IP multicasting in the network adapters will pick it up and say, oh, I've got a subscriber for this message, let's grab it and read it and pass it on to the RVDs. So multicast is very efficient if I got it available. It's a pity it never really took off. I had high hopes for things like Netflix and that using multicast and saving a huge amount of bandwidth, but it never took off in a wide area model. So then what we've got here, so this RVD just gets the message and the topic it's been published on. So in this world, when I subscribe by doing a call on my local daemon. When I subscribe, I don't go up to the publisher, I subscribe locally. And every message published goes to here, and it takes care of saying, do I have any subscribers interested in this? If I have, I'll pass it on to them. So I'm getting local filtering. I think that says that on the previous slide. All participating systems receive all the messages at about the same time, which is really good if you're doing stock prices or something. And the filtering is all done on the receiving system, receiving RVD, who then pass it on. And the subscriptions are done locally as well. Nice system. What happens if we want to go over a wide area network, and we assume we don't have any wide area network multicast support? There are standards for it, they are implemented. Let's assume we don't have them. Then what we have is yet another little daemon, the RV remote daemon, and it gets the messages just like these local ones do, and it talks over the wide area network to another RVRD, which then does a local multicast to the systems up there. So exactly the same model, but we just have a little relay step in it. Right. Highly decoupled messaging style. Yep, publishers don't know about their subscribers. Subscribers don't know who's publishing. Can't get much more decoupled than that. And publishers and subscribers can sort of come and go. That's all cool. Reliability, security, transaction support, performance. If you're trying to build a whole system around that, these might be challenges. I said TIBCO does do reliable messaging in a sort of way because they need to. Security in that model is incredibly hard. All the messages are being sent to everybody. How do I do security? And the answer is we use encryption, and when you subscribe, you get part of your subscription. The subscriptions are validated, and then you get a decryption key for the messages. So this works. And performance is great unless you start doing things like asking for reliability and logging. Okay, message brokers. That line I had before where I said Well, what format are these messages in was a lead into this slide and this topic. So I've got 4 legacy systems and something driving them up the top there. And in format there means internal format. It's our local messaging format. You know, we've got together and we've decided here are all the things we want to be able to have as messages, and we've got a Bible of messages. This is all the messages we have. Our internal format. This is how we order eggs for breakfast. This is how we order bacon. We've agreed. We've had committee meeting after committee meeting in the organisation to agree on all these message formats. That's all cool. Internal formats. So we have some source of requests coming in. They generate messages in this internal format. And then I want to pass them on to legacy systems that were around before we had all this standardisation of internal formats. You know, new systems, they're fine. They're native with internal formats. They're cool. But we've got legacy systems as well that we don't want to spend the money on rewriting. So each one of these is going to have a piece of code in front of it which knows how to transform the message from the internal format to the format that the legacy application can understand, and then we'll just go and call the legacy application. So we're just going to, we've standardised, because it's a good thing, on internal message formats, and then we'll have a translation layer for each application between internal format and legacy format, and backwards if we're sending back results as well. That sounds simple, doesn't it? What happens if we want to change the one of the message formats in our standard formats? You know, things are going to change. What happens if the APIs to the legacy application changes? Yeah, you just imagine a lot of maintenance work happening here, and this is going to be a constant. If I change the legacy format, I've got to go and change this piece of all my legacy systems to make them match. Could be a bit messy. Well, as all those little bits I had down there are basically the same, why don't I just make them the same? Why don't I write a piece of code which knows how to translate from internal format to legacy formats? That's all it does in life. So it's a single thing. So I have a thing called a message broker, and its job in life is to do these translations. So it's going to be a horrible piece of code. That's okay. We can probably automate most of it. So the clients up there pass messages down to the message broker, and the message broker translates them appropriately and sends off the requests out of that. So we've centralised that transformation. And that's good. That's a good model. Such a good model that they're commercial tools in wide use, because we always have this problem. And they're called message brokers. And they're part of EAI, Enterprise Application Integration, because we always have lots of lumps and they all talk different things, and we've got to bridge the gaps between them. So in Enterprise Application Integration, we're trying to integrate lots of enterprise applications. So message brokers are a good tool for using that. So the initial message brokers just did what I talked about, transformation. Okay. This is the eggs order message in our internal standardized format. This is the legacy applications order eggs message, and we'll translate between the two. Cool. And that's what they did. You normally, in those tools, don't go around writing lots of horrible code. You'll have some way of specifying abstractly that message format, and someone will take care of doing the mapping for you. Or you might even have nice GUI tools that'll let you go and just describe how to map between the two things. And then that was useful, and then people thought, oh, why don't we add to that? Because I might want to do something a bit more complicated. So they started adding rules engines and intelligent routing. So you say, well, I get this message, and when I get that message, I need to take this half of it and send it across to here, and that half send it there, and take the results and join them back together and send it back off to there. So I can start doing simple business processes. I can do if then else's, business logic, because it's all message based anyway. You can imagine the type of thing that your business analyst does with drawing flowcharts and things. You can implement that directly. And adapters. So one of those boxes down there is SAP. I'm sorry for you if it's SAP, but it's SAP, you know. Well, everyone's using SAP or Salesforce or something. Well, we know what message formats they want. So I can supply you with an adapter which talks to them. So a lot of the hard work has already been done because they're in wide use. So someone's already commercially making available sets of adapters to large commonly used products. And typically, but not necessarily, but typically they'll be built on some type of messaging layer because I need some type of plumbing to join all these bits together, and we've just said how good messaging is as a plumbing layer. So they'll be built on a plumbing layer. So message transformation often have graphical message format definition tools, or there might be some standard, you know, perhaps I can do XML definitions, or there'll be ways of defining the transformations, and they'll do them efficiently. Route messages based on content, rules engines, and then they morph in. So we started off doing this. This was a useful thing to do, so we added some more functionality, and then now we're talking about workflow engines. We're defining whole business processes. They're the same, there's no real breakpoint between them, but they just morphed and evolved to become business process or workflow engines. Where now I can talk about high-level business processes, and I get this type of request in, and it goes to this business process, and the results of that go to this one, etc. So abstract, but executable. I don't write any code. I can describe my business process in nice GUI tools, and then push the run button or the compile button, and out pops an executable version of my business process. It actually runs. And there are even standards in this space, a thing called BPEL, Business Process Execution Language. And so if your tool's using BPEL, a lot of them will have it as an option. Then you can define your business process and then say publish it, and it will publish it as a BPEL spec. And you can take that BPEL spec and load it up into a different workflow execution engine, and it should run because BPEL is a standard. So, get back there. Wrong button. One of the examples I'll give you in a couple of slides' time is BizTalk Server, which was Microsoft's entry in this space. And obviously this space now, there's cloud-based versions of them, etc. But BizTalk Server has its own internal format for describing business processes, one which makes it easy for them to go and do the GUI tools and the execution. But if you push the publish button, it writes it out as BPEL. So we can take BPEL. And IBM's tools the same, and other tools. You know, so you could imagine defining your business process in one manufacturer's system and then transporting across and running it on someone else's because of the standardization. Typically, these would be hub and spoke architecture, so there'll be a box which does this, and it receives input messages and writes output messages. Here's a couple of screenshots of, this is from IBM's product. This is an MQ, message queuing based tool, and we can draw pretty pictures, we can drag things from here over to here, we can link things together, etc. It's all pretty cool. Here's a BizTalk example. Here's the types of primitives I have, and I can drag these across and connect them together and put ifs in and things, and then somewhere or other I can say run this. So what I'm joining together is larger boxes, components. I've got big chunks, components and applications. A message comes in here, gets sent to this system to process that, etc. And I'm describing that level of system. The word sometimes used is orchestration, which conveniently happens to be written on there. This stuff is also called business process orchestration. I think I mentioned adapters before. Adapter is a thing which lives between that message broker and the target system, and it can either how we do that translation, and they can be arbitrarily complicated. Right. Okay, this is a nice slide. So I talked about application integration, EAI, enterprise application integration. We've got all these bits. We want to get them to talk to each other. So if we just had one business process, and this guy talks to that one, and that one, and that one, and that one, sequentially, for example, then we've got one overall process, we've got 4 interfaces, that's cool. But that's probably more likely where I've now got 5 processes and they all talk to each other. Here, this guy is the centralized hub. It's controlling the business processes, and you go and do that, then that one. So everyone just needs to talk to this guy. This is a general point-to-point model, and everyone's talking to everybody. And if you go back to the hairball I had in that first slide, it's closer to that, except it's much worse. So that spaghetti architecture, that should say n squared. I don't know what happened to that suffix there. N squared interfaces, and it's just horribly complicated. So with one of these, oh great, we'll put a message broker in. That way we'll centralise all those interactions. So instead of A talking to B and B talking to C, they all talk to the message broker. That's conceptually simpler. So on the outside here, I have 1, 2, 3, 4, 5, but in the middle we still have the big pile of spaghetti. So someone still has to know how to translate if necessary and how to route, etc. But perhaps it's better because we've now got a single tool and a single way of describing all those interactions. Perhaps we can have rules and routing and things in there that'll make life easier. Well, perhaps we don't need all that translation anyway. Perhaps we could just standardise and say, we'll just have a single set of messages, and all my applications will use the same set of messages in the same formats, and there will be no problem. Everyone understands what a purchase order looks like because we've defined the standard purchase order. There you go, no problem. We'll have an enterprise data model. We'll define a single set of messages that will be used everywhere. That's a great idea. Any problems with that? No? Anyone being cynical? That's good. I don't know how many times I've heard IT managers, CTOs saying, oh, I'm going to do this. And a couple of years later, they never talk about it again. As that last thing says. Getting agreement is going to be the hard part. Great idea. And the other fad is we'll just have one database. Everything will be in one database. That'll make life easier as well. Yep. And I expect the other version will be, we'll just have one set of services. we'll just go and we'll do service-oriented architecture, and we'll just have a uniform set of services everywhere. That's probably going to work well too. For CTOs. Okay, we're getting close to the end. That's good. So message brokers, really useful tool. They can be very efficient. They're very flexible. They can let you abstract a lot of that complication and put it in one place where you can manage the complication. And as long as you understand what they all are, at least rather than being hidden, they're up front saying, I need to work out how this is going to work, so at least I can get to think about it. Single point of failure questions, scaling questions come in, but they're probably easily replicatable because they're not going to be stateful. Failure, you'd have to handle failure by having a lot of the messaging infrastructure being persistent and transactional. The rules-based engines know about transactions. They'll do in BizTalk Server, that I played with a bit. You define a business process. You define compensators for parts of the process. It will automatically run. If something fails, it will go back and unwind the business process by running compensation. So that Saga's model I talked about when we did the transactions, they know about that and will provide support for it, which is pretty cool. Any number of vendors would be happy to sell you their software. Okay. So this is just summarising what we're talking about. So there's a few slides here on various messaging patterns. So queues, nice, asynchronous. The quality of service is highly configurable, and it's nicely loosely coupled between the clients and the service. Pub sub model, the published messages sent to everyone who's subscribed to the topic, the lots of options about reliability, and you get efficiency if you can use multicast, broadcast, but it still works with point-to-point, and lovely loose coupling. Brokers, it's effectively a hub and spoke architecture where the broker's the hub and the senders and receivers are the spokes. You can do quite interesting, complicated things in the broker. You can abstract large amounts of that integration question into one place and have tools to manage it. And continue that on, you can go to full-fledged workflow engines in that middle bit. So there's no real difference between that and that, apart from that we're just doing much more robust things in there. We're not just doing message transformation and acting as a hub, we're actually putting the business processes in that spot. But we still get nice encapsulation, and because we're putting lots of good stuff inside that workflow engine, and we're getting loose coupling because we're just calling on the services. The services know how to process an order. They don't know what the overall business process is because that's not their code. You can imagine taking that type of system, the purchase system where we do get quote, place order, send invoice, etc. All those steps, those little yellow boxes at the bottom there can be doing all of those, and they're nice. They're nicely encapsulated pieces of functionality, and the whole thing is integrated into the overall purchase workflow because of that workflow engine. It knows how to string all the beads together. And this is the last slide. Back to where we first started from, you might think, oh, that RPC stuff, sort of, why would you use it? Well, of course, everything is built on top of something much like RPC. It might, in the WCF world, that's the API you see for some of this stuff, but deep down, we're doing local or remote procedure calls everywhere. So the underlying glue is still that stuff, but now we've built abstractions on top of it to make life easier for you. And that's probably, oh, there's some references. Yeah. Okay, speaking of references, next week I get to talk about web services And there's a whole chapter in Ian's book on web services. I know. I wrote it, that's why I know. Okay, so that will do me for today, and we're actually 2 minutes early, which is good, rather than 5 minutes late. Okay, and you have a lab tonight. The lab tonight is playing with message queuing. I hope it all works. It worked on my laptop, so I hope it works on the lab machine. Let me turn. Everything's a message. So the message from here we're talking about that extra one comes from the queue messaging. So RPC is there, RPC underneath RPC, we're passing messages in whatever protocol using whatever protocol. So we're extracting upper level to queue messaging, where we now have queues of messages, and then we have more useful attributes then of real other messaging and persistent messaging. It's gone up a level of abstraction. In the WCF world, it's all just done by transport bindings. So you keep the same API, you just decorate it. Whereas if you're going other worlds, in Java world, you say, oh, the API for sending a message is that. It's not an ordinary RPC type call, it's a different program.
The adapter you're talking about, is that a piece of hardware? Or
Sorry?
Is you're talking about adapters?
No, they're the software.
Okay, it's a software.
Yeah.
Okay.
So it might be a SAP adapter.
Okay.
Salesforce. Or
Okay.
whatever. Yeah.
And also, with the publisher subscribe thing,
Yeah.
You said that the publisher doesn't retain a reference to the subscriber, right?
All these things are yes, except if they do.
Okay.
So in that TIBCO model, if you're doing the TIBCO model and you're not doing security, then it's purely multicast.
Yeah.
You drop on the
It's
network.
like reminds me of like an event bus.
Yeah, exactly.
It's an event
Yeah,
bus. Yes.
it's an event bus. Yep.
Yes.
It's an event bus. Yep. But as soon as you want to start doing things like vetting your subscribers, then it's got to be passed up to someone who can do the vetting, of course. If you're doing security, then you've got to have the two-way communication to
Right.
encrypt the messages and
Okay, thank you.
yeah, so it's an event model.
Yeah.
It's a good word to use as well.
Okay, thank you.
Put your laptop down.
So I'm looking at this recording data and output sector and if the rising to after the experiments is finished. And then there was one point saying don't measure your test harness.
Oh, of course, yeah.
I don't know.
Well, so test harness is the code you're using to run the test,
yeah.
right? So you've got to be careful that that's not what you're actually measuring. So
why would you measure a test case?
Accidentally.
So you're okay.
Do this. So if you're something on one of those slides that said you typically will have here's my client systems,
Yep.
and they're running on some number of boxes.
Mm-hmm.
Over here, an entirely separate box
Yep.
is my system under test,
Mm-hmm.
and they've got to be a separate box. Otherwise, the client activity will disturb what I'm measuring on the server. Because if they're running on the same box,
Mm-hmm.
then the clients are busy using processor time,
Right.
and well, the server's trying to use the same processors.
Yep.
So they interfere with each other.
Okay.
So if we ran it all on one box,
Yep.
then what we'd end up doing is that our server results would include the overhead from the test harness itself.
Yeah.
And And when you're doing working out exactly what to measure as well, you've got to be careful that you're not including your measurement overhead in the results, because measuring takes time.
Yeah.
So you want to be careful that your measuring isn't.
Like the initial setup.
You're not measuring your measuring.
Yeah.
Yeah.
Makes sense. And another thing is, so when we actually, so we want to gain confidence of our measurement, and you mentioned that for narrow range we want to sample many executions transactions.
Yes, let's say you're down here in the load.
Yeah.
Up here in the load, it's a bad place to be, right?
Yeah.
Because something is causing that drop off.
Yeah.
But if you're down here in the load, then if you did lots and lots of measurements, you send a request, get a response, and do it 100,000 times and measure each one, then your latency, your response time, will probably be pretty much a normal distribution.
Yeah.
But if you only do 2 or 3 measurements, you've got a spot here, spot here, spot here. You don't know what the distribution looks like. So it's normal stat stuff. The more measurements you make, the better defined is your distribution.
Yeah, but why does that relate to so what narrow range is it actually referring to? Is that like this one?
What Alan or Alfonso meant by narrow there was a well-defined range.
Okay. So you only want to have many measurements in that range, and outside of that you don't care?
No. Narrow meaning how well-defined is it?
Yeah.
So if you...
like how accurate the result is?
Yeah, how well-defined is it?
Oh.
So if you do one measurement, it comes back with a second, you say, oh, I've got 1 second response time.
Yeah.
And you do it again, and you get 2 seconds. Well, you don't know whether it's 1 second or 2 seconds, because you don't know what the distribution is.
Yeah.
If you do 3 measurements, you start getting an idea of the range, and the more measurements you do, the better defined that range is.
Okay. Yeah, I misunderstood.
Yep.
What?
But once you're up here,
Yeah.
then that distribution is going to get... It's probably not going to get... see if I can... These distributions are often not normal. Okay, but let's assume that it won't be normal. So it might be like that, but it's... When it gets really heavily loaded, it's more